Hi everyone, so today I'll be teaching how a CPU works. So to begin, the CPU takes information or requests from an input device such as your keyboard or your mouse. This will then tell your operating system what kind of data needs to be retrieved. And then this data will be retrieved from your storage device, such as your SSD or hard drive. After that, these requests will then be sent from your hard drive, like the data and all the information, to RAM or random access memory. RAM is just a temporary and easier storage for information accessed by the CPU. From there, your CU will then determine what kind of information or data it needs to be requested from RAM, and then it will be sent from the RAM to the CU. This data or information will be stored within the registers within the CPU for quicker and easier access. These are temporary registers, so they don't permanently hold information. After that, the CU will then decode the data that it needs, and then send this data along with instructions to the ALU. The ALU would then perform a series of calculations and logical operations that then utilizes the registers to temporarily store the results. After that, the results are sent back to the CU, and the CU will either use these results or send these results back to the RAM for quicker and easy access, or back to the hard drive or SSD for permanent storage.
Hello, everyone. All right, let me break down something that sounds more complicated than it actually is, which is the fetch, decode, and execute cycle. This is the heartbeat of every computer, like your laptop, your phone, even your gaming console. They all do these three steps repeating like indefinitely, nonstop. First thing we'll start with is fetch. Fetch is literally the computer saying, what's the next thing I'm supposed to do? So instructions. It goes over to its memory and it grabs its next instruction, brings it back to the CPU, which is our computer processing unit. You can imagine it like checking the next step in a recipe or looking at the next line on your to-do list. It's nothing fancy, it's just fetching the next instruction. Then we'll move into decoding. The computer processing unit looks at that instruction and tries to understand it. To the computer, instructions are just numbers, like 0 1 0 1 0 1. It needs to translate that into, oh, this means add two numbers or move this data or, jump to a different part of the program. It's basically the computer reading the recipe and figuring out what it's asking for. The last step is actually execute. This is the part where the CPU actually does the work, where it executes and goes through with the recipe, like I was talking about earlier. If the instruction, for example, said to add something, it will add it. If it's set to move the data, it moves it. And if it's set to compare two values, it compares them. It's literally like doing the step in the recipe, just mixing the ingredients, turning on the stove, however you want to describe it. And then as soon as it's done, the computer immediately goes back to the first step and repeats the whole thing again. So it fetches, decodes, executes, fetches, decodes, executes. It just loops this cycle millions or even billions of times per second, of course, depending on your computer processing unit. So even those computers seem like really ridiculously complex, underneath it all, they're really just repeating a simple three-step process super fast. That's the fetch, decode, execute cycle, and it's literally how everything on a computer runs. That's about it. Thank you for listening to my fetch, execute, and decode cycle.
Hi everyone. So I'm going to be covering over the three fundamental logic gates as well as logics. So first up, we have AND gates, and I've gone ahead and made some examples. So here you can see that AND gates require both inputs to be 1 to get an output of 1. So you can see that when we have 0 and 0 as inputs, the output is 0. Same with 1 and 0 or 0 and 1. The only combination that gives us an output of 1 is when both inputs are 1. So going over to OR gates, you can see that it only requires one input to be 1 in order to get an output of 1. So looking at these examples, 0 and 0 still gives us an output of 0, but everything else, as long as there's an input of 1, you'll get an output of 1. For NOT gates, they're pretty straightforward. If you input a 1, you'll get an output of 0, and if you input a 0, you'll get an output of 1. So these are very straightforward as well. So now let's go over adders. Adders are a little bit more complex, but still simple enough. So in this example, you can see that if you input two numbers, it gives you a sum and a carry as the output. In this example, we have a input of 1 and 1 as an input, which gives you an output of the sum being 0 and a carry of 1. By the way, this is all done in binary. If you want to add more than 2 bits, you'll need a full adder. With a full adder, as you can see here, you can have an input of A, an input of B, and a carry over from a previous operation. This lets you chain together additions together beyond what a half adder can do. You still get a sum and a carry out as well, and I've gone ahead and included a table here of the possible outputs that you can get with these combinations, so you can go ahead and take a look. And yeah, that pretty much just covers the 3 fundamental logic gates, as well as how they can be combined to create adders. So yeah, thank you.
Everyone. So I will be giving a quick overview on memory hierarchy. This is going to include information about registers, cache, RAM, as well as secondary storage. So I created a little diagram representing specifically just speed and proximity to the CPU. This has nothing to do with the real hardware you would find in a computer. So to start off, we have registers. So these are located inside the CPU. And out of all the memory types, this is the fastest by far because of the fact that it's so close to the CPU. Purpose of registers are typically just to hold data that is currently being processed by the CPU. So this can be some kind of arithmetic or any other instruction-based operation. Now we have the cache. So cache is typically static RAM, and this is located on the CPU or near the CPU, which is why this is the second fastest out of all of the memory hierarchy. So the purpose is to store copies of most likely to be used memory or most frequently used memory. And the cache is much faster than the main memory, much slower than registers. Oh, another thing about registers is that the only downside is that they have very limited storage. Now for the main memory or the dynamic RAM, this is typically found on the motherboard. Now RAM itself is short for random access memory. And so basically the purpose is to store any bit value or just any data, and any random piece of data within the RAM could be accessed at any time. Hence the name, random access memory. All RAM is volatile. That includes dynamic RAM and static RAM, which means that without power, the data can't be held. The 2 different forms, which are static and dynamic, like I said before, are used for different purposes. Static RAM is typically used for the cache because it's fast, much faster, but it's much more expensive as opposed to dynamic RAM, which is typically used or referred to as the main memory because of its density, so which means it stores much more data compared to static RAM, and it's a lot cheaper. So for secondary storage, which is the slowest out of the bunch and typically the farthest from the CPU because it's actually external. So we have any kind of external technology like SSD, HDD cards. These are non-volatile, which means that it can be used without any electricity, and their purpose is typically or specifically for long-term storage outside of your computer.
Hello, so I will be giving an explanation of this short example I have here of the MIPS assembly language. This is the language we use throughout the course. So the syntax for this example right here is load word. This is the destination, this is the offset, and this is the base address. So the destination is where what you're looking for will be stored. The offset is how far from the base address you're going to go. How far from the base address you're going to look. And then the base address is where you want to start looking. So yeah, this right here would be putting whatever's at the location T1 into T0. The fetch step is when you input the command. The decode is when it takes it and transfers it into machine language which it can understand. Then when it executes, it would do what I said earlier. Put the information located at T1 into T0.